Okay, I'm going to look at problem 6.17. Here's the problem statement, and the diagram is just right here. Basic idea here, you have a block that's at rest, and what happens is you drop it. So here's the block, here's its rest. It's 2 meters above the spring. You drop it, and then it goes down, hits the spring, and causes the spring to compress. Okay. Now, what will happen is you'll get some oscillations of this. It would push the block back up, of course, after it gets to its minimum point, and then push it up, then down, and then eventually would stabilize. But what we care about in this problem is just that you drop in the block, lands here, compresses it. We want to find the point where this is compressed the most. Okay, so we have to think about this. And first, looking at it, we need to define some variables, or at least define one variable actually in this problem. What we'll do is we'll say we'll take its height, 2 meters, and then we'll add a distance called x, which is how much the spring compresses. Okay. And here's the actual quantities that go with it. Um, we have a 3 kilogram block. It's dropped, so it's not in motion at the beginning. The spring is undeformed, okay, so it has no energy associated with it, right? It's just undeformed, so we expect this drops it, it causes it to deform. And we're giving it spring constant with that, okay? Okay, so let's take a look at, so we're looking for the deformation of the spring, x. We're given a height, I defined it as h. We're given a mass of the block, and we're given the K value, or the spring constant for this particular spring. Okay. Now, one of the things we have to apply here is the so-called first law of thermodynamics, which basically states whatever energy you have in a system, you can't create. You can only convert energy from one form to another. You cannot create it from nothing. Okay. So that with that in mind, that's actually going to give us an equation that we can follow. And this is basically, if we go back to looking at energy, when we looked at work and energy, there's a certain amount of energy associated with the block. Okay. It has some kinetic energy, and kinetic energy meaning whatever initial velocity it has at the top, and potential energy. And potential energy could be in terms of like lifting it off the ground, it could be stored in like a gravitational field, or it could be stored in some kind of elastic energy or chemical energy. And in this problem, there's no like potential energy stored chemically. So we have its initial kinetic energy, initial velocity, plus its potential energy, sort of stored energy. And this is at some position, right? It really doesn't matter in the system where it's defined, but we're going to define this as at the top when it's at the highest point where it actually starts from. And that's equal to the kinetic energy plus the potential energy at the second point. And the second point that we care about is just where it compresses the spring all the way. Okay. So any kind of kinetic energy due to its motion, plus any energy stored in a gravitational field um, as its weight, and which is just basically its weight times its height. And this also would include any energy stored in the spring. Okay. So if we just uh, take a look at that. Here's our initial kinetic energy equation. Here's our potential energy stored in the spring. And here's our potential energy stored in like gravitational field, or the weight of the object, okay? So it's weight times whatever position above its reference point um, that we care about, okay? So we need to think about, what that value of H is for this one. Okay. So one of the things we can do is just take these two ideas and plug them into the equation. So we have some initial kinetic energy, some initial potential energy stored in the spring, an initial energy. I actually wrote this as G here, so I wrote as gravity. That's really essentially this. Should be G if you want to write this as G or W, either way. Okay. Um, so this is the weight part. Okay. So it's whatever's energy stored in the spring, whatever's stored in gravitational field, essentially its position due to its weight, and then whatever kinetic energy it has in its second position, and then its potential energy or whatever energy stored in the spring being compressed, and this one is the gravitational field or the weight. Okay, so let's just see if we can simplify this. First part of this is what we recognize is it has no velocity at the top, right? It says it's initially at rest. So that's going to be 0, okay? At the moment you drop the block, the spring, as defined by the problem, is uncompressed. So there's no energy stored in the spring also. But there is energy stored in the gravitational field or weight of the object because it's lifted up by a certain amount, okay? Off a reference point, off the ground, or any real reference. We just need a reference point. Then we're going to look at its final. So this is the second position. This is when the spring is fully compressed. This is the second position we care about. Again, at this point, the block dropped, it accelerated, it went down, it had velocity all the way through. But when it reached the bottom, it has no velocity anymore. So we have no kinetic energy at the bottom. Then the potential energy stored in the spring. This is the compression of the spring. So the spring's been compressed. We now have potential energy stored in the spring. And the last one is gravity. Well, our reference point we're using is basically our 0 point is the bottom of where the spring bottoms out, essentially, where in this case the spring goes to lowest level. So at that point, when it's at its lowest level, we've defined that as being 0 also. Okay, because it's the potential energy in gravitational field is only relative to whatever we call as a reference. So our equation becomes this. Here's due to the weight, and here's due to the part due to the spring. Okay. Okay. So what we're going to do is our h now becomes just 2 plus x. And x is how far compressed. The 2 is the 2 meters that was given. The x is how far is that spring compressed. Okay. Equals whatever energy is stored in the spring. Since the spring was uncompressed, there was no initial energy at the beginning. There's only the energy due to it being compressed, which is the x. The distance or the compression, amount of it was compressed or stretched was defined as x. Okay? So what we can do here is just rewrite this equation. So I rewrote it, put everything on one side. And the form I'm going to set it up in, of course, is just I'll set it up in the form that with a, b, and c as our coefficients. And then, as you notice, it's a quadratic, so we can use the quadratic formula to solve for the value of x. And we'll actually come up with 2 values for x, okay? So all I did was just substitute in for k and 1/2 and mg over here and 2mg here, okay? So here's the form. Here's the formula you use. And, you can use a calculator or go through and actually plug the numbers in. Here's my 29.43. Here's my 29.43. Here's 4 times A, which is 565. And C was, oh, well, 29.43 was negative, right? So it's a negative negative. And this is just squared, so it really doesn't matter. And A was positive, C was negative. So this is really an addition operation being done here. So you plug those values in and then divide it by 2a, and then what you'll come up with are 2 answers, right? Because 1 for the plus and 1 for the minus. And you're going to come up with x is equal to 0.350 meters and also minus 0.298. Both of those are solutions to this equation, okay? But what we recognize is that this one doesn't make any sense. A negative compression, it's not, negative is not like a stretch because that's also a deformation of the spring. So the only one that really makes any sense is the positive value. Okay, so we keep the positive value, and here's the final answer, 0.350. And that's that problem, 0.350 meters.